Okay, in 1986, I was home from a break in college and all by myself home watching. The parents were off at work and I was on a break, and I was watching TV. PBS came on, and this was the very first time I ever saw Julius Sumner Miller. Didn't know who this nuts old guy was. But I was in physics in college, so I would have been in my sophomore year. And he was rolling these things down the ramp, and every time I thought something was going to happen because I was in college physics, something different happened. It was driving me crazy because I hadn't really seen that before. I hadn't really thought it through all of the way. And so I want to talk about Fushigi Ball physics. And when you're doing that, I would highly recommend that particular Julius Sumner Miller episode where he's rolling objects down. And it ran across this Fushigi Ball who I'd never heard of, which I'd never heard of. It was in my garage. My wife had got it at somebody's garage sale and thought my son might enjoy something that levitates and is anti-gravity. It's not. And I was like, give me that. I'll find some reason to use it. And I did. It's a latex sphere, and inside of it is a metal sphere. And I've seen these cut open on other YouTube videos and the like, and I think it's hollow in the middle. And I don't think they're all manufactured the same depending on when they were manufactured. But I've done many a lab on that because I spend way too much time on rotational stuff. And you can predict its radius of gyration based on its downhill rolling characteristics. So let me give you an example of what I mean. There is in one of my Giancoli textbooks, and it's not in the most modern version, a radius of gyration, which tells you if all of the mass was at that radius, it would give you the same roll characteristics. What is that radius? And so if you put this on the ball, on the ramp like Julius Sumner Miller did, and I have a ramp here I use for many things with start line, and you put that on there with a hoop or that on there with a disc, you can have the students predict which one's going to win and why. And this would usually outrolls most of them because it's not a solid metal sphere in the middle, but it gives it enough heft in the center that it lowers the radius of gyration. So the way I have that particular lab set up is your gravitational potential energy up the ramp, when it gets down to the bottom of the ramp, some of that energy is 1/2 mv squared translational rotational energy, or translational kinetic energy, and the rest of it is rotational, 1/2 I omega squared. And you can do that to determine a value for K. For example, if your I omega was mk squared for I, and K is the only variable left, and omega squared is V squared over R squared because you made that substitution. You could do some math here, and you can take a screenshot of this or something and get a value for K, which is not quite 3.3 centimeters. You have to do some substituting there, some rearranging and substituting, but you can get it. Another thing we did with that is I invented, it's not in this lab, but there's another lab. It must be in the next week, which would be week 3-6. Let me see if I can find it real quick. Okay, that's radius of gyration, which is in textbooks. But let's say I want to compare that to 1/2 mv squared, or 1/2 mr squared for like a disk, or 2/5 mr squared for like the big sphere. That was the St. Regis that's in one of my other videos. Or 2/3, which I think would be for a hollow sphere. I invented a coefficient of rotational inertia K, where I could put that K in front of your mr squared, and your R being the actual radius on this, figure out from circumference. And then you could compare that K value to these other ones and see where it fit in the ranking as to who rolls first based on the size of this coefficient. So that one's one that I made up, coefficient of rotational inertia, but you could use it. It's got a good theoretical basis. There isn't any reason why you can't use it. And in that one, my equations end up looking different, and it ends up as 0.74, which was interesting because when I got the result back from that, it didn't make any sense. And I reasoned that the only way I could get that number was if the table I did the lab on wasn't level, and I pulled out the level, and sure enough, it wasn't level, and it wasn't level by about the amount I would have predicted. So I found out that I had a flaw in my setup that I didn't know I had.